Later came the case of the disappearing and reappearing particle, which we had the honor of collaborating with Yakir, in which there was something even more interesting. Take such three boxes like that, and then make the right post-selection, and now you have a very strange prediction. You have three boxes. At T1, you are sure, you are confident that it has resided in box 1. At T2, should say perhaps ABC, at T2, it has certainly resided only in box 3, which is remote from 1 and 2. There is a possibility of passage between 1 and 2. And at T3, it certainly resides in box 2, which is, again, adjoined with box A. So here we have two boxes in which it certainly resides at a certain time. Certainly, they are empty at the next time, the same particle, and then it resides there. How can you prove that? So here is just the ontology which Aharonov employs. Actually, you have this negative particle, negative ghost particle being in one of them, and such that when the negaparticle and the particle are together, then it's not an annihilation, but they, for brief time, they seem not to exist, such that the boxes are empty. As we know, there is always a problem. How do you verify predictions of the TSVF? You can make a measurement because you would ruin it. Here is a trap. You make a measurement at the beginning, at the morning. You make a measurement at evening, and then you are assured that something very interesting happened at noon. But what you can do to prove it? You can't open the boxes at noon. It is only by that you later retrodict that this is what happened. We joined two Japanese physicists to do something amazing, which Aharonov and Lev did. I'm missing here, I believe, I'm missing here the paper. But Aharonov and Weidman showed that in some cases, you can make not a weak measurement, but a strong projective measurement in order to show that a particle is at two places at the same time. This is the famous shutter experiment, in which you make a double slit experiment, and then you send a particle, a test particle, to the two slits, and it is being reflected by both of them, and this has been even shown. This is what Okamoto and Takeuchi did not many years ago. Along came Lev and said, let's visualize it, just in terms of the interferometer. And here comes the nested MZI, similar to the Mach-Zehnder interferometer, with the difference that there is a smaller MZI in the middle. Now, what you do when you send a particle through this system, then you're going to get here where it goes. So here you have your fake future. You see, the detector D never clicks. So it didn't go there. Only detector D2 clicks. So there is only one trajectory which apparently the particle could follow. Now you run it backwards and you get the ridiculous fake past. Here you have these two fake futures. Now when you run it backwards, you have the fake past. It has taken the other trajectory from which it didn't come back, and it has a strange history, a strange origin, which is completely ridiculous. Ridiculous again, but when you combine these two, let me skip the formalism, when you combine these two, you get something really, really strange. At the right-hand part, for a very brief time, there is a particle. The particle didn't go there. The particle didn't come back from there, but it was there. Can we prove it? Then Cohen and myself joined forces with Takeuchi and Okamoto and said, let's make an experiment. Now not with weak measurements, but with strong measurements, with projective measurements. And here is, here is the shutter experiment by Weidman and Aharonov. So we combined all of them and we made a synthesis. I apologize for this ridiculous drawing of mine. There is a more professional one by Okamoto and Takeuchi, but here it goes. Let's take another particle, a test particle, split it into 3, 4, 5, not only in space, but also in time. Just give them a delay. And then look what happens. The test particle tells you. So here is how we overcome the problem of verifying a TSVF. You make a measurement at the morning. This is the pre-selection. You make a measurement at the evening. This is the post-selection. What do you do at the noon, where the interesting things are happening? You can't make a measurement because then it won't be between two measurements. So you can either make a weak measurement or do what Weidman and Aharonov did, take another particle, let it interact with it in a very subtle way, put it aside, get your post-selection at evening, and then come back to what happened at noon and inspect your particle. And this is what our test particle tells us. Either it went through this path, never found the photon there, never found the particle. It was reflected by a mirror back here. Either at noon it went here and it met a particle. It was bounced by a particle and came back. Or either it went inspected this part and didn't find a particle. Here we have something very interesting. Here we have a new ontology which tells you that for a very brief time, negative mass exists between pre and post selection. What does that say about our universe? Are there many worlds? Perhaps. Lev is sure, many of you are sure that there is. What I want to call attention is that whether there are or there are not, in this world, there is a very interesting physics waiting to be explored. This is our paper, non-local position changes of photon revealed with Okamoto and Takeuchi, and our results are going to come. Here is his talk, and let me finish only with this, about which I'm alone. I don't think that even Aharonov agrees with me. This is Lev's nested interferometer. This is our bomb testing experiment. Notice that here in the detector that tells us that this is fake future and the photon never went there, I could place a bomb. I strongly believe that we can generalize it. That is, that every time that there is an interaction-free measurement and there is no click, but still that no click leaves traces, something along these lines has happened. There was an exchange of a particle and a negaparticle. What you think that nothing has happened actually has happened. Now, people may say, and Lev may say, you can't prove this in the ordinary Mach-Zehnder interferometer. It's a completely different mathematics. And then my argument will be the following. The light rays coming from a distant star are bent by the sun. We can see it only in an eclipse. I have no doubt that it happens also when there is no eclipse. In other words, I am sure that although there is no way yet to generalize this ontology of the TSVF to a general physics, which tells us what is a collapse and what is an interaction-free measurement, what is a negative result, something very exciting along these lines is happening. Here we have many papers which we wrote during this time. Thank you very much, Lev, for 30 years of very fruitful dialogue, and thank you all very much. Nathan Argaman, do you want to say something retrocausal?
Your description still distinguishes between what's happening at this time, at noon, as if what will happen later will not affect it? Or so do you think that retrocausality could perhaps help explain this?
Sure. This is retrocausality. I have a problem with that, which I never resolved. I do believe in becoming. This is a question that I've been asking here. I rose up at morning from my bed. I was struggling on the way on the Ayalon because I was late here. And later, I hope to be back home. Is the previous Avshalom and the present Avshalom and the next and the future Avshalom, all of them coexist? I know that Nicolas Gizet believes in some kind of becoming. I also believe in some kind of becoming. At present, this has to do with philosophy. I'm interested to know whether many worlds people also believe in that. But yes, most of our work with Cohen, with Aharonov and all that involve retrocausality. What I want to say is that the ordinary methods of interpretation of retrocausality, say Kramer and Roth-Kastner and so on, I wonder why they do not pay attention to these kind of experiments. Sorry for being too long. So let me say only this. There are many interpretations of quantum mechanics, many worlds and others. Something there is unique about the TSVF, and here it is. It gives you many, many predictions. Surprising. When you analyze them, you say, oh, sure. It also accords with standard quantum formalism. Here is the fact. No other interpretation of quantum mechanics. Bohmian mechanics, many worlds, and so on. None of them is so rich with new predictions as the TSVF. Does that mean that the TSVF is the best interpretation of quantum mechanics? I said that here is a very strong argument in its favor. It is only TSVF that surprises you as Clev. And then after that, you say, oh, yeah, we could know that through one-state vector formalism. You understand what I'm saying? And here, I think, is a very strong example to that.
I just want to kind of investigate the rhetoric a little bit. You said, okay, here's no ontology, and I guess for certain purposes, no ontology is certainly not enough ontology. If you want a physical account of the world, you've got to postulate something. Then you said, oh, here's too much ontology, right? You had many worlds in Bohm. And then now you have some, you know, maybe retrocausal two-state, whatever it is. It has some ontology. I don't quite understand how you're making these judgments. You would agree that a Bohmian account of all these experiments where there is a single particle and it follows some single track and there's no fake future that's doing anything. All the causal stuff is being done by a quantum state and particles in accordance with well-defined differential equations, and they'll give you all these predictions. And you say, well, that's too much. Or, I mean, I kind of don't understand what is too much about that ontology? What is excessive?
I was not meaning any disrespect. Okay.
But too much means there's something wrong with this.
No. I say only, you know, we know the problem. We heard, say, in the previous talk, can you prove that other worlds exist? So here is it. Can you prove that an empty wave exists? You remember Vigier and all these people for many years asked whether you can prove that this kind of guide wave, empty wave, which actually would contradict the uncertainty principle, and they gave up, or perhaps some people did not. So I would say there is excess ontology with a lot of respect. Let me say another thing. I think that they are very fruitful. Let me quote a PhD student of mine, Shachar Dolev, who once I heard him analyzing a situation along the many worlds interpretation. I said, do you believe in many worlds? He said, no. But very often when you have a difficult problem in quantum mechanics, analyze it along the lines of many worlds, guide wave, and so on and so on. They are all very good. I still argue that the TSVF is the most fruitful one. I was not meaning any disrespect, not even to Copenhagen. It's beautiful, it's elegant.
But, yeah, this is what I'm so if one's interested in ontology, then an approach that says, I'm simply not, I mean, I better not assert there's no ontology. That's really bad. You can say, I just don't care about ontology. If you're interested in ontology, that's not a good thing to do. But let me just very quickly, if someone were to say, look, of course there's evidence of, quote, empty waves, just plain old two-slit interference, right? Plain old two-slit interference tells us something or other is sensitive to whether both slits are open.
Even interaction-free measurement, yes.
Yeah. I mean, so it's not like that you would say there's no evidence. I mean, if you're doing it in this theory, you say, of course there's evidence, just interference phenomena. That's why we come up with a theory like this.
It is just that every evidence in favor of the guide wave, of the Bohmian mechanics, is just as good for many worlds interpretation and for Copenhagen. So it's not bad. All I'm claiming is that during all these years, one approach to quantum mechanics, one formalism, the two-state vector formalism, keeps surprising us with many, many new results that you can show. They are not against, they do not contradict the quantum formalism. In retrospect, they all turn out to be in full agreement with it. I said that this is the most fruitful one. No disrespect to any of the others.